Now, we've looked at column vectors previously. Mostly we've dealt with column vectors with 2 or 3 components. Now we're going to look at n vectors. We're going to look at general properties of column vectors that are true no matter how large the vector is. So we just use this denotation n vector to denote some column vector, and n will be the length of the column vector. Now, notice this notation. A1 is the first component, where 1 is the superscript. An is the nth component. So these are not powers, these are superscripts. It should be clear in this section that we're not taking powers. Of course, when you deal with linear mathematics, you don't take powers. So in this section, if you see a superscript, that doesn't mean power. It means that that's the index that tells you which entry in the vector that particular component is. Now, we've already seen how to add and multiply vectors, so we can pass over this quickly. We're just showing here the same rule that we did for 2- and 3-dimensional column vectors. To add components, add vectors component-wise. To multiply each component of the vector. That is, to scalar multiply each component by that corresponding scalar. The zero vector is the vector of all zeros. If you plot this plot vectors in a graph, then the zero vector corresponds to the origin of your coordinate system. Now, we've referred to hyperplanes previously. In this section, we're going to do a more thorough discussion. What we want to do is generalize some geometrical notions familiar from 2 and 3 dimensions to higher dimensions. For instance, line. Now, if you take a line in R2 or R3, it's actually determined by 2 vectors. One's a displacement vector and one's a direction vector. So here see this equation that L equals U plus TV, where T is in R. So what does that mean? This U is what we could call a displacement vector, and TV is the direction vector. So how does that work? Well, I've drawn a picture here so you can see. Here we said that U plus TV, and I said U was the displacement vector and V is a direction vector. So here's my U right here. Oops, it's not giving it to me. Let's try again here. All right, well, we just have to pass that. So U is my red vector and V is my green vector. Now U takes me out to the line and U gives me a point on the line. Now, then I can add any multiple of V. V lies along the direction of the line, and any multiple of V plus U will give me a point on the line. U plus TV. Now, I did this in 2 dimensions, but you can imagine doing the same thing in 3 dimensions. You have some displacement vector in 3 dimensions, and then another vector that determines the direction, and along that direction gives you your line. Now, what you can do in 2 and 3, you can do in higher dimensions. You can't graph it, but you can imagine that the idea is the same. So we just call that higher dimensional object a line in higher dimensional space. So here's an example of a displacement vector plus t times a direction vector. Now in this case, t goes along the x-axis. So you can imagine this is a line in 4 space that is parallel to the x1 axis. He's doing the 4 components as x1, x2, x3, x4. All right? All right, now, that's one direction vector. Now, suppose we have 2 direction vectors. Here are 2 different direction vectors, u and v. And here you take both of these as direction vectors. So if I take some multiple of u and some multiple of v, I'll end up somewhere in this plane that contains u and v. For instance, if I take 1/2 u plus 1/2 v, 1/2 u will take me out here, 1/2 v will take me up here, I'll get a point here. If I take 3/4 u plus 1/3 v, I go out 3/4 this distance, and then I would go up parallel to this v, 1/3 of that distance, I'd end up in a point here. But any point that I take that's a linear combination of u and v will be in this plane. Now here he says 2 non-zero vectors usually determine a plane. So when don't they determine a plane? If the vectors are in the same line, then you're not going to have two different directions and you're not going to have this flat region. Okay, so, all right, so that's how it works with two vectors. All right. So just a reminder how adding vectors works. You take the first vector u, second vector v. U plus v is the result when you put the tail of v at the head of u. Now, if I take some multiple of u, then I'd go u farther along here, and then some multiple of v, I would go parallel to this vector to get another resulting vector. And you can see no matter what multiple of u, what multiple of v, you're always going to end up with this plane. Right. Now, in the example here, we also had a displacement vector and one direction vector. I said here we have two direction vectors. We also need a displacement vector. So you can take one displacement vector, two direction vectors. We can kind of see how that works in 3 dimensions as follows. Scroll down here. All right, so here I've drawn 3 axes, x1, x2, and x3. This vector here, this red vector here is my p. Right? And then here I have 2 direction vectors. You kind of have to imagine this, that these are not in the flat plane, but they're in 3-dimensional space. And then there's going to be a plane determined by these 2 vectors. I can't really draw it, but again, you kind of have to imagine this plane would look something like this. Okay. But it's displaced from the origin. It doesn't contain the origin because this p takes me out away from the origin. Okay, so we have p plus 2 direction vectors determines a plane. All right, here's a numerical example in 6 dimensions. Again, you can't graph this, but mathematically or algebraically it works the same way. Here's my displacement vector, and you have 2 direction vectors. These 2 direction vectors happen to be along the first 2 coordinate axes. Now, it doesn't necessarily have to be that way, but in this case it is. All right. So now we've talked about lines and planes with 2 dimension. Now, why not, instead of 2 direction vectors, have a larger number of direction vectors? And that's where we get into a hyperplane. So here we have the definition of hyperplane. Here we have 1 displacement vector, k direction vectors, and the hyperplane is determined by the displacement vector with no constant plus a linear combination of the direction vectors. Okay, so this is a straightforward generalization of how we did this plane and the line. 1 displacement, linear combination of direction vectors. Only in this case, we have more than 2. We have k direction vectors. So this would be a k-dimensional hyperplane. The dimension refers to the number of vectors in the linear combination. Now, we saw that there's an exception if the 2 direction vectors up here are actually parallel, then we don't get a plane, we only get a line. So there's a condition on the direction vectors. As long as the vectors are kind of independent. In other words, none of the vectors can lie in the k-1 dimensional hyperplane determined by the other vectors. All right, so this is a k-1 dimensional hyperplane. Here we have 0. This is a k-1 dimensional vector hyperplane through the origin. If the jth vector vj is contained in this hyperplane, then the hyperplane determined by v1 all the way up to vn will not be k-dimensional, but k-1 dimensional. All right, so here's an example, good example here. Here we have 6-dimensional vectors, and here's my displacement. Then here I have 3 vectors. Now you can notice that this vector plus this vector is equal to this vector. So this vector is actually inside the plane determined by these 2 vectors. So in this case, we do not have a 3-dimensional hyperplane, only a 2-dimensional hyperplane, because any vector in this set can also be written as a linear combination of this displacement vector plus these 2. This doesn't add any more information. So we only have a 2-dimensional hyperplane in this case. Now, when you talk about a plane in 3 space, the plane is 2-dimensional, 1 less dimension than 3. All right, so if you say hyperplane in an n-dimensional space, typically you're referring to an n-1 dimensional hyperplane. Right? Technically, formally, every hyperplane will have a number of dimensions, but if we don't refer to the number of dimensions, we'll just say k minus 1. So for instance, if you're in 7 dimensions and you talk about a hyperplane, unless I specify the dimension of the hyperplane, I mean a 6-dimensional hyperplane. Right? So that's it for this video.